Hey guys, I said that I give the mathematicians a little bit of a proof. So today I'm going to prove a bit more rigorously that the potential is equal to minus big G m over r. Now when I did this in the last video, I kind of lied a little bit to you. The argument I made wasn't really mathematically rigorous. It does work. I said that force times the distance is equal to a work done, and therefore we could have minus gmm over just r is equal to a work done, and then I said that potential was just work done per unit mass, so we had minus gm over r. And like I say, although that works to give us our potential, which is a big V, it's a bit of a cheat. I'm lying to you. It's not really how big boy physicists do it at uni. So I'm going to show you how you actually do it, and it's much more insightful, I think. So what we do is we start off with something or someone with a mass m at some radius r away from a planet. So this guy has a mass m, and he wants, if you like, he wants to fall towards the planet. But we said the definition of our potential is something like it's the work done per unit mass in order to move this guy from r away from the gravitational influence of this mass, which will mean moving him from that radius r to somewhere over here where r equals infinity, and therefore there is no force, and actually that means there's going to be no potential either, but we'll ignore that for a sec. But at infinity, if there's no force, he can't be acted upon gravitationally in theory. So here's what we do then. If we want to know the work done as we move this guy from here over to infinity, obviously gravity is going to be acting on him the whole way. So because gravity is acting on him, we know, and this is kind of the argument I made last time, we know that force times the distance he's moved through is equal to some work done. Okay, but as he moves, the force is going to be changing on him, and because the force is changing on him, that means we can't just do this simple multiplication, because at every point it's a different force, so we can't just do that. It's cheating. So instead of that, we say that the work done on him is actually equal to the integral of the force, which is a function of r. Yeah, we know that because of Newton's universal law of gravitation. It's a function of r. Everything else in this equation is going to be constant. I'm not changing the mass of him or the planet. G is obviously a constant as well. So it's going to be an integral with respect to distance, which is radial. It's r in this case. And it's going to be from a radius r all the way to r is equal to infinity. So that's how you calculate the work done in actually moving this guy from there to there. So I'll just write that again there. That's f function of r dr to infinity from r. Now we said that potential, so I'll get rid of this now, we said that potential is actually the work done per unit mass. So it's the work per mass, which means I have to just add an extra term to this integral. I have to add 1 over m. So that's it. That's all we've got to do. Now we can get on with the integral. We have everything we need. So if I shove in my equation from over here, my function of r, my force, that's going to give me 1 over m. Got the integral from r to infinity. and that's going to be substituting in minus GMM over r squared dr. And I'm just going to stop there, and if you want to have a go at this on your own, pause the video, have a go, see how you do. Okay, so I'm going to carry on with this. And you can see actually the first thing that we've got here is that my mass divided by mass here cancels with this mass here. Awesome, so that simplifies it a little bit. I also have some constants, so all of these things are constants, so I can actually pull them out of the integral, which again will simplify things greatly. So now I've got minus GM, the integral from r to infinity of 1 over r squared dr. So if I perform this integral then, that's minus GM. The integral of 1 over r is the same as integrating minus r to the minus 2 dr. So same rules as always, you're going to drop, you're going to raise the power and then multiply by that factor. So I'm going to raise it to minus 1 and then multiply by minus 1. So that will give me minus r to the minus 1 between r and infinity. I hope you've seen this notation. So my square brackets now is my integrated function, and I'm going to basically set the limits of r to infinity. So from there, minus gm is going to be equal to, so I can substitute in infinity, so that's going to be minus 1 over infinity minus, so plus 1 over r. Now obviously 1 over infinity gives us something infinitesimally small, so that's going to be negligible, it's going to be 0, so I can get rid of that, and that just gives me minus gm, and then in brackets 1 over r.
Good morning, students, and we're halfway through the week, and I hope you've been having a brilliant week.
Awesome.
Yes, my voice is back, so sorry if you don't want me, but I'd just like to wish a very happy 18th birthday to Emily Watson in Wilbraham. I do hope you're having an amazing day, and it'll be as special as possible. Bye, students, and have an amazing day.
Cheers for that. Happy birthday to Emily Watson. So if we just go back to the top then, all of this integral is equal to the work done per unit mass. So we can say that this integral now is the potential at a radius r, and that is equal to minus big G m over r. There you go, boom. So this is the cool thing about physics at uni actually. When you do this, everything we do at A level then becomes integral or differential forms, and it just makes so much more sense. So hopefully that was insightful for you, and you can see really where this comes from, where this idea of potential comes from, and why it's negative. And by the way, it's negative because to get this guy from here to here, I've got to lose some energy. So I've got to burn thrusters, lose some chemical energy or something. Okay, so that was just a short video. Next up will be orbits, so I'll see you then. Goodbye.